Algebra 2 students, this is the lesson for section 2.1. Please grab your yellow Learning Objective State Standards page and you'll see, hey, concepts 2.1 is not listed. And that's because section 2.1 is background information. It's something that you've already learned in the past, but you have to be able to do it in order to cover the rest of chapter 2. So we have to start here, and we have to remind ourselves about all the vocabulary that comes with what we're going to study in these sections. So we have relations and functions, and we're going to graph relations and identify functions. Up here at the top, we start with relations. Relations are any graph. It doesn't have to have anything fancy about it. Anytime that you graph something, you are graphing a relation. Now, relations, just like anything that we graph in 2 dimensions, have inputs and outputs. And typically we use X for the inputs and Y for the outputs, but that doesn't have to be the case. It can be any 2 variables, inputs and outputs. But there's a special name for the X's, the inputs, and the Y's, the outputs. The X's are called the domain, and the Y's are called the range. Now what's important to note about that is that D comes before R in the alphabet, and X comes before Y. There are a lot of things in math where that works. Also look back to input and output. I comes before O, so input and output, domain, range, X, Y. And literally that's what it is. The domain is, they're the inputs. What variable did you use for the inputs? For us, a lot of times it'll be X. And then the range, outputs. What variable did you use for that? For us, it will be the Y's. So there are 4 ways to represent relations, different ways to see what it is you're supposed to graph. This is the one we really like. Those are ordered pairs. So the first number tells us whether or not to go right or left, and then the second number tells us to go up and down, up or down. And how we determine that is by whether or not there's a negative. So in the X's, if you have a positive number, you're going to the right. And in the X's, if you have a negative number, you're going to the left. And then for the Y's, if you have a positive number, you're going up. If you have a negative number, you're going down. So there's a set of ordered pairs. Now, what we see to the right of that is just another way to represent that. That's called a mapping diagram. It's kind of like a couple of ovals, but you'll see the numbers here have these arrows to show us where they're supposed to go. So if you put a -3 in, you get a 4. Well, that's exactly what we have right here. If you put a 3 in, you get a -1. That's exactly what that says. It's the ordered pair 3, -1. Put a 4 in, you're going to get -1. Yep. And you'll also get a 3. And there it is. So we can see that a mapping diagram tells us the exact same information that our ordered pairs told us. It just looks a little different, that's all. So this is another one that we like when we have to graph, and this is a table. So a table of values. Notice it's the exact same ordered pairs that you see in the others. And then last but not least, this is why we have all of those things, is so that we can graph. And this little graph here is called a lot of things, and the main name for it would be the Cartesian coordinate plane. And that is after a gentleman named René Descartes, who came up with this process in the 1500s. So we've got the Cartesian coordinate plane, also called the XY rectangular plane, but we graph. That's what we do. And like I said, most of the time, we use the X's for the right and left and the Y's for the ups and downs. So now, problem 1 says, let's think about what's going on here and think about the different ways that we have to demonstrate this. When skydivers jump out of an airplane, they experience free fall. At 0 seconds, the skydiver is 10,000 feet above the ground. At 4 seconds, he is at 9,744 feet. At 8 seconds, he is at 8,976 feet. At 12 seconds, he is at 7,696 feet. And at 16 seconds, he is at 5,904 feet. Where for me, that would be where I would finally take a breath after screaming my head off for the first 16 seconds. So how can we represent this relation relation in 4 different ways. The first thing that we had were ordered pairs. I mean, that's what we like to graph. So it said at 0 seconds, we're at 10,000 feet. And notice I'm not going to use an extra comma for the 10,000 there because that would confuse people when you already have a comma in your ordered pairs. And at 4 seconds, we have 9,744 feet. So notice how all this information is coming at us in twos. Here's the time. The next one that they have up there is 8 seconds. And then here is the distance. And then we have 12 seconds, 7,696 feet. And scrolling this up just a little bit, that last one is 16. And 5,904 feet. So each of those lines up so that you can see the 0, 4, 8, 12, and 16 is all talking about time. And then over there with the 10,000, 9,744, etc., those are all going to be in feet. But now they want me to do the others as well, and I know I write too big, so I'm going to go ahead and go to a new page here. And I remember that it was 0 and 10,000, and then we had 4 and 9744. Then we had 8 and 8976. We had 12, and that was at 7,696 feet, and 16, and that was 5,904 feet. Now, the reason I wrote this in the 2 columns is because the mapping diagram was another way that we could show how this works. And again, it's just kind of rounding off rectangles is really what it is. You can make ovals, it doesn't matter. But here's the important part. We have to show this x goes with this y. And then, table of values. Well, we can see all the numbers right over here. We're going to use time as our x's, and then we'll use the distance, lining these up. Like so. Now, what we probably really want to see is what's going on with that graph. So here is the mapping diagram and the table of values. You can use the table of values, you can use the ordered pairs, whatever you want to use here to get these graphed, because that's going to be our final method. So this little thing right here is 20 by 20. I'm going to try and darken this up just a little bit so that we can see the blue a little bit better. There we go. And since it's 20 by 20, and I know that I'm not going to have any negatives, because you can't go a negative time and you can't fall a negative distance, I can use that all as the first quadrant. Now, what I'd want to do is think, hey, I better label here. This one's going to be my time in seconds. And then up the vertical side, I would have the height in feet. I didn't leave myself much room. Maybe I'll try and write it sideways. Height, feet. There we go. All right, so now I have to figure out what I want to go by, what kind of numbers I want to use. And I see that my x's go up to 16, and I know I have 20 little blocks, so I'm just going to go ahead and make each one of those blocks 1. But I'm not labeling every single one, because then it's too hard to make out what was written. So I have it nice and labeled, but I'm not going by ones when I write this down, so that it doesn't mess anybody up and they can't read what I have. Now the harder part is going to be figuring out, okay, how do I do this 0 to 10,000 on the other side, and do I want to start with 0 or don't I? Well, 16 and 5,904, Well, that was the lowest that this ever got. So what I might want to do is put a break in the graph, and that's just a little jagged cut there. Some books will use what look like a couple of parallel line segments to do that. But that says I'm going to leave a little bit out here. And I think what I will do is I will make every 4 units here count as 1,000 to spread this out. So I'll start with 6,000. And then this would be 6,500, and this would be 7,000. And then I'd have 7,500 and 8,000, 8,500 and 9,000, 9,500 and 10,000. Now, while I'm thinking about it, I better come up with a really good name for the top here. And this is all about skydivers, and they are free falling. So I think I'm going to name mine Skydiving Free Fall. Because what you really want is everything labeled so that there's no mistaking what on earth it was that you were doing. What is it we're graphing? And we can see the time in seconds along the bottom, and then we can see the height in feet up the vertical side, the left-hand side there. So I need to graph 0 and 10,000 way up here, 4 and 9,744, which would be just short of 9,750, 8 and not quite 9,000, 12 and a little bit more than 7,500. I can't stand in front of it or I can't see where to graph. And then 16, not quite 6,000. So about like so. And yeah, we can definitely see, hey, there's falling going on here, you know, and we're not going to connect it up. We were just supposed to graph it, and that's what we did. And we have all the labels and everything is appropriate for what we have. Now, what you never do is start adding more grids because you didn't put enough spots on to get everything to work out. So let's just say that I had to graph 20,000, and I get here and I realize, oh, I only have 10,500. Well, you better erase and you better start over because you have to use the space that's allotted to you. So that means you have to do some thinking beforehand about how you're going to put those numbers on there. Now, problem 2 says, let's go back to what we began talking about in here, and that was domain and range. So my domain, that's all my x's, and we make what's called a little Richard Nixon bracket there. And we put all the values that were in the domain. Now, those were our times. Those were our x's. So that's our 0, 4, 8, 12, and 16. And what you do is you separate them with commas. And then you make another backwards Richard Nixon bracket. If you look up Richard Nixon, one of our presidents, former presidents, and he was in fact impeached, but he resigned before any of that could go through, and you will see that that looks a lot like his profile. If he were just standing to the side and we saw his shadow, that would be a lot like his shadow. And then D comes before R, so X's come before Y's. So we go back, and I am going to put these in order from smallest to biggest. So it was 5,904, and then the next one that we graphed was 7,696. And notice I'm not putting commas in for those thousandths places. 8976, 9744. And 10,000. So really important that we take off those extra parentheses so people can see what those numbers were. So domain, the inputs, x's, range, the y's, the outputs. So there it was. In this case, our time ended up being our domain, and then our height in feet was our range. Now problem 2.5 says list the domain and range for the following parabolas. So now we're starting to get to the point where we have to look at pictures and say, okay, what's going on here? So what I want to do is look at this first parabola and ask myself, is that ever going to stop going right and left? and I see that the arrows show me no, it's going to go forever. So what I have to put is all real numbers. And you can write those 3 words if you want to. But in math, we have a symbol for all real numbers, and it's an R with an extra line on it. So that would be all real numbers. Now, it's not using all the y's. In fact, right here is the lowest y it ever gets to. And that lowest y is -1. So my y values are going to be greater than or equal to -1. And that's how we describe what's going on there. So why don't you pause and try the middle one on your own. Hopefully with this one you saw, yep, the arrows are showing, going slightly right and left forever. And for this one, the range right down here at -3, so y is greater than or equal to -3. Now, both of these first 2 parabolas happen to open up. Pause the video and try the third one. This one, again, the arrows show right and left forever. However, this time, right there at y equals 3, that's our cutoff, and it's below that. So y is less than or equal to -3 is how we describe the range. So domain and range don't just come from a listing of numbers. It can be from a graph, and we can see those. We need to think domain is x's, that means right and left, and range is y's, and that means up and down. Now, this says blank is a relation where each element in the domain, the x's, corresponds to blank, one element in the range y's. These are special. This is not just a relation. This is called a function. So functions are special because for every x in the domain, there is exactly one y. For every input, there's exactly one output. So what I have to do is go through these mapping diagrams and ask myself, for every input, is there exactly one output? So I look at A, and I say, if I put a 2 in, what am I going to get? Well, the arrow shows me just a 1. That's one number, so that's okay, but I have to check them all. I put in a 4, and I get a 1. Still just one number, so this is okay so far. I put in a -5, and I get a -3. One number. This is all good. So this is a function right here. This is a yes. So which of the following are functions? I guess I don't want yes. I'm going to write down function. There we go. Now I go to B. And for this one, I say, all right, if I put an 8 in, what do I get? A 6. That's one number. It's good. Put a 1 in, I get a -7. That's one number. Put a -4 in, I get a -9. One number. This one is also a function. Now I go to C. I put a 5 in, arrow shows me I get a 6. Uh-oh. If I put a 1 in, I get both a -7 and a -9. That's not okay because for every input there has to be exactly one output. In fact, let me switch colors here because this is not a function. Every input has exactly one output. So take a look at the D values. See if you can figure out whether or not it's a function or not. So I look at it and I think, okay, in D, you put a 4 in and you get a -1, 8, a 6, 1, -1, 6, 6. Uh-oh. If you put a 4 in, you get both a -1 and a 1. Not a function. I look at E. Put a -7 in. You get one number. You get a 14. Put a 9 in. One number. -7. 14. One number. A 7. Put a 7 in. One number. 14. That one's good. That one is a function. And then we get to F. And this is tougher because it said for every x there has to be exactly one y. And then I realized, well, that's not tough at all because this is not a function. If I put in -2, I get 2, and I also get -1. That's not okay. That is not a function. So it turns out when they line up vertically, up and down, then it's not a function anymore. The other 3 points are okay, because there are no points above or below it, straight above or below it, that would match it. But we've got that negative x equals -2 that's going to cause trouble because there would be 2 different numbers kicked out of there. Now, in this got it, it says give an example of a function. You can use any of the 4 ways. You could use ordered pairs, mapping diagram, table of values, or graph. So go ahead and make something up. You can hit pause. You can do that. All right, so we wanted a function. Most people go to the last one that they just learned, and they just put a bunch of points on here that don't have any other points that line up with them vertically, above or below them. And that's a good idea. But there's so many different ways. You know, we had 4 different types that we could do. Ordered pairs, mapping diagram, the graph, obviously, and then we had table of values. So any of those. Now, problem 4 says, which of the following represent functions? And I remember that if I have points that line up vertically, so up and down from each other, it's a no. That's a major no. Not a function. Oh, I don't want to use green. Green usually means go and good. We don't want that. Not a function. It was right here and right here. And it turns out if that happens anywhere on the graph, it's a no. So now I'm looking at B, and I'm trying to see, is there anything lined up above or below? Hey, that one's good. So this one is a function. I do the same thing with C. Try to figure out, is this one going to be okay? Yep. It's not crossing 2 points. So this is also a function. It's not crossing 2 of those blue points. So there's an easy way to tell, and I've been talking about it as I went through here, and that is, do they line up vertically? And it's called the vertical line test. If a vertical line passes through more than 1 point, then the relation is not a function. And then it says, why does the vertical line test work? So think about that for a second, and I realize that when 2 points line up vertically, they have the same x-coordinate, but different y's. But different y coordinates. And that fails the definition of a function. So it fails the definition. For every input, there is exactly 1 output. Now this says draw one graph that shows a function and one that's not a function. And we got to see some of those up there earlier. So I think, okay, let's see. Green function. Red, not a function. Oops. Writing too fast. My hand's not keeping up with my brain. There we go. And all I do for a function, same thing I did before. I'm just going to pick some points and make sure that there are no other points that line up directly above it or directly below it. So that one's a function. Not a function means that that can't happen. So there have to be at least 2 points that are going to be lined up vertically. I'm going to make an oval like that. That is going to fail the vertical line test big time. So something along those lines that lets you know, hey, I know what I'm looking for here. It has to pass the vertical line test. Now, how do we write these? Because these are special. These are functions. For every input, there's exactly 1 output. And to do that, to show people that this is special, we use what's called a function rule. And it says it's an equation that represents an output value in terms of an input value. And if you're looking at this, you should be saying, well, that's exactly what we did when we studied linear algebra. Because it is. That's exactly what we studied. So if we had y equals 3x plus 2, we would go ahead and make an x and y table. And we got to pick what went in for the y's. So we just decided, and most time you did -3, -2, -1, 0, 1, 2, 3. You know, if you didn't know what it was going to look like, that's what you did. So you pick those. And then the y comes back out. Now that you don't get to pick. The y comes from the fact that you must use the formula, the equation, and that will give you what your y's are. So notice that the x is the input, and that's called the independent variable. You get to pick that. You get to choose. It's independent. However, we do not get to pick the output. The formula tells us what that's going to be. So that's the dependent variable. It's dependent on the formula. What did the formula say to do to your x value? Now, to show somebody that we're actually talking about a function, passes the vertical line test, for every input there's exactly one output, we replace the y. We use function notation. So like it says, we use f of x instead of y to show the equation represents a function. So you can see y equals 3x plus 2, and then the next time you see it, it says f of x equals 3x plus 2. And y equals negative 2x minus 5, f of x equals negative 2x minus 5. It is just notation. Don't let it mess with you. Remember, f of x is just y. That's all it is. So it's really just the output. But it's fancy to let people know, hey, this is a function. This is not just any relation that happened out there. It's a function. So it's special. So problem 5 says for f of x equals negative 2x plus 5, what is the output for those three numbers? And the first thing I think of is, well, let's go back to the old days when we made a table. And then I realized, oh, I don't want that f of x thing there. That's going to mess me up. I'm going to change it to y. And then I can just do what I always did, which is take the number and plug it in. So if I take negative 2 times negative 3, because that was the first number in my table here, and I add 5, what do I get? Well, negative 2 times negative 3 is 6, and 6 plus 5 is 11. Then I try 0. Negative 2 times 0 plus 5. Well, negative 2 times 0 is 0, and 0 plus 5 is 5. Now, 1/4, that's going to take a little bit more thinking. Negative 2 times 1/4 plus 5. Well, negative 2 is the same thing as negative 2 over 1. You can either do your cross reducing with the 2 and the 4, or you can just do top times top, bottom times bottom. It's going to say negative 2/4 plus 5, and your brain goes, oh my gosh, that's negative 1/2. So negative 1/2 plus 5 is 4.5. Or you could write it as 9/2. Remember, you take the 2 times the 4 and you add the 1. So either way, for graphing, you'd probably want to leave it at 4.5, so you can figure out exactly where that is. All right, so hopefully you're thinking, well, I can do this because I know that f of x is y. I'm going to change that to y, and then I'm going to put negative 2, 0, and 5 into the equation and see what I get. Please do that. Pause the video, then double check. For the first one, if you put a negative 2 in, we have negative 4 times negative 2 plus 1. Negative times a negative is a positive, so that'll be 8 plus 1, which is 9. Negative 4 times 0 is 0, and 0 plus 1 is 1. Negative 4 times 5 will be negative 20, and negative 20 plus 1 would be negative 19. So there it is. We're just learning that f of x is not scary. F of x is just the way to write function notation. It's y, it's output. So when trying to write a function rule for a real-world problem, so a word problem, determine which variable is dependent and which one is independent. Again, independent is the one that you get to pick. But dependent is the one that is determined by usually the cost. So problem 6 says a pizza costs $14 with a flat delivery fee of $1.50. what function rule models the total cost of the number of pizzas delivered? And now here's something that you need to know, and that is we don't have to use f of x all the time. And in word problems, sometimes we like to change them. So I'm looking at A, and again, I always think about what's the last thing they told me to do. They want the total cost of pizzas. So cost, I'm going to use P for pizza. I'm not going to use X in this one. So if I want the total cost, I start thinking, well, I have to pay $1.50 no matter what, because that's the delivery fee. And then I have to figure out how many pizzas I want, because those are 14 each, 14 a piece. So that means that's my variable. That's what's going to change. I get to pick that. So that means that the P in this equation is going to be the independent variable. So that's the function rule that models the total cost of the pizzas. And now what I have to do is figure out what would it be for 5 pizzas. So I'm going to lose that C of P so that I don't accidentally do math over there, because this is not for math. No math. This is just notation. That's all it is. And now I want to put the 5 pizzas in. And 14 times 5, going to cost us a little bit. So we've got $70 plus $1.50 for delivery, $71.50. And it depends on what kind of pizza you're getting, whether or not that it's expensive to you or not, you know. If it's your favorite pizza, maybe you don't mind that 5 pizzas cost $71.50. If you're buying for just a bunch of hungry people that don't care what it tastes like, then maybe you want to go someplace a little bit cheaper. Got it. You are buying bottles of a sports drink for a softball team. Each bottle costs $1.19. Yeah, they don't want to say Gatorade. What function rule models the total cost of the purchase? Oh, all right. Well, then I'm going to do cost, and I'll use B for cost per bottle. Oh, well, it's just $1.19 each. $1.19 for each bottle. So 1.19B. And that's a function rule. And again, B, the bottles, is independent. I get to pick that. And now it says, let's figure out 15 bottles. Now, I want to introduce you to the fact that we could have written it like this. The cost of 15 bottles. That's our fancy function notation. But again, we don't want to do any math on the left-hand side. So we want to put the 15 in here, $1.19 times 15. And then you could always grab a calculator if you want to, or do that by hand, however you feel about it. And that would come up to $17.85. So here is another new way to say, I want those bottles to be a 15. Because notice, all I did was replace the B up there with 15. And we could, at the end, bring that back and say, all right, now that we know that we didn't have to do any math over there, the cost of 15 bottles is $17.85. All right, so the major objective of this section was just to remind us what relations are, how we graph, all of that good stuff, input, output. And again, it's not on our yellow concept sheet because it's stuff we're supposed to know from the past. So there is the assignment, and that should go really pretty quickly for you because, like I said, a lot of this is just review. So do a good job.